My name is Samir Khan and I'm an application engineer here at Maplesoft. I speak to our customers and help them use our software. This talk is about solving technical problems quickly and efficiently with parallel computing and multi-core math. Before I start, parallel computing sounds very much like a computer science concept, something a software engineer would do. However, if you're using Maple, you may already be using parallel computing concepts without even realizing it. For example, Maple automatically multi-threads many common matrix computations. This is the agenda for the next 20-25 minutes. I want to give everyone some sense of why and how Maplesoft have implemented parallel computing and multi-core math, what that means for our users and our future plans. I've also prepared a Maple worksheet with many parallel computing examples, a parallel programming tutorial, benchmarks, and several other items. I'm not going to demonstrate this worksheet during the course of this webinar, but if you'd like a copy, please send us an email. We'd be more than happy to send you a copy. I'd like to start today with a real success story. This is a user story in which parallel computing made a real tangible difference to the quality of life of scientists and engineers. Oxford Instruments are based in the UK. They're a high-tech company that research, design and manufacture superconducting magnets. These devices, these products are used in highly demanding applications such as NMR analysis machines. Accordingly, their design and construction must be precisely controlled. Oxford Instruments scientists do their design calculations in a Maple worksheet. These worksheets contain a large number of analytical computations, and often the worksheet takes a long time to compute. This is compounded by the fact that these worksheets need to be recalculated, often with small changes in the design parameters. They sent the worksheet to us and asked us to find ways of making the worksheet more efficient and quicker. We found that we could parallelize many of the computations in the worksheet. Typically, on a quad-core computer, this reduced processing time by a factor of 3. That's a real benefit, a real tangible time savings. Their scientists now spend less time in front of a computer waiting for a calculation to complete and more time designing a better product. So, why are so many scientists, engineers and mathematicians interested in parallel computing? Why do they want to make sure that their math software is multi-core aware? Well, let's look at this plot. On the y-axis we have processor clock speeds, and on the x-axis we have years from the 1970s. For many years, CPU manufacturers progressively released newer CPUs with faster clock speeds. This meant you could make your math software run faster simply by buying a new CPU with a faster clock speed. However, at around the year 2000, this trend faltered. Processor speed stabilized at between 2 and 3 GHz. Why is this? Well, as you increase the clock rate of a CPU, you need to provide more power, and that power produces heat. That heat has to be dissipated. If you crack open your laptop or your desktop, you'll find that there's a fan attached to the CPU. That fan spins and removes heat. However, by about the year 2000, CPU manufacturers found that you couldn't remove heat fast enough using air cooling. They had to find other ways of making their CPUs fast enough. In a parallel trend, CPU manufacturers had increased the sophistication of their processors so that they did more work in a single clock step. However, this wasn't giving their users the performance gains that they needed for their technically demanding applications. So about the year 2000, they started releasing newer CPUs with more cores. But this meant you couldn't make your math software faster simply by buying a new CPU with more cores. That math software has to be reprogrammed in order to take advantage of this new multi-core computing power. And that presents a real challenge to companies like Maplesoft. Our goal is to provide our users with the software they need to complete their technical computing tasks quickly and efficiently. So who are our users and what's their typical user profile? Well, typically, mathematicians, scientists and engineers use our tools. They use Maple to automate repetitive math-based operations. They may write a few simple programs or they may script some batch operations, but they essentially don't see themselves as programmers or computer scientists. They simply want high-level productivity software to help them solve technical problems more quickly. They don't care about low-level computer science concepts like thread safety, memory management or task allocation. Now, as a company, we've embraced the technology of parallel computing. This benefits both novice users and power users. Even minor performance gains, when compounded, make a real difference to the user experience. A second here, a second there, it all adds up. And this culture of parallelism stretches deep and wide into Maple. So we're not just implementing new multi-threaded math routines, we're actually revisiting our existing functionality and making it compatible with multi-core CPUs. We're also making deeper changes in Maple which yield performance gains all over. So how have we serviced new multi-core CPUs? Well, we automatically parallelize many common commands such as matrix computation and polynomial manipulation. I'll speak about these in detail later. If you want to write your own parallel programs, we provide two parallel programming languages, the task model and the grid model. We also support CUDA technology. This allows you to offload math operations onto your graphics card. And we also sponsor research labs to write parallel programs for Maple as well. Now, Maplesoft have a team of highly experienced software engineers and developers, but if I were to nominate a subset of those developers who are responsible for our parallel computing infrastructure, it would be these four gentlemen. They're all highly respected in their fields, but I'd like to spend a couple of minutes introducing you to each of them and their work. This, for example, is Jason Shelby. He recently defended his PhD thesis in parallel memory management in applications that dynamically allocate memory, and his expertise is making its way into Maple. Darren Ohashi is our parallel computing evangelist. If you go to mapleprimes.com, you'll find many blog posts written about the benefits and pitfalls of parallel computing. He's also responsible for developing our parallel programming language. Dave Linder is our numerical performance expert. He integrates the latest third-party parallelized math routines into Maple. And this is Paul DeMarco. He's our expert on parallel computing, distributed parallel computing. He's recently run Maple on a Cray supercomputer over 16,000 nodes. We'll learn more about this project later. So let me speak about some very specific parallel computing and multi-core math features. Matrix computations and linear algebra are at the very core of science and engineering, and many of these operations can be easily parallelized. For example, Maple automatically parallelizes floating point matrix multiplication, inversion, linear system solution, and certain decomposition methods. Maple splits these calculations across as many cores as you have in your computer automatically. There's no user intervention required here. So for example, in this snippet of Maple code, I'm generating two random 4000 by 4000 floating point matrices, and then I'm multiplying them together. Maple automatically distributes this calculation across all of the cores of your computer. And if you're on a Windows computer and you open up your task manager, you'll find that your CPU usage shoots up to reflect the usage of all of the cores. Maple also automatically multi-threads many polynomial manipulation operations. Now, polynomials are a fundamental building block of many computer algebra algorithms. They may sound quite niche, very specialized, but they're actually used in high-level Maple functionality. So, for example, if you've ever used the simplify command to simplify the appearance or the mathematical structure of a Maple expression, you may automatically benefit from automatically multi-threaded polynomial manipulation. Specifically, polynomial expansion, factorization, division, and multiplication are parallelized, and these benefits stretch across Maple. Here, for example, I'm expanding a high-order polynomial and timing how long it takes to compute. Now, Maple will automatically split the calculation of this across all of the cores of your computer. However, there are tools in Maple which allow you to restrict the number of cores Maple uses as well. If I restrict Maple to using one core, this calculation took 2.7 seconds on my laptop. If I allowed Maple to use 2 cores, it took less than half that time, 1.2 seconds. Again, that's a real tangible time savings. The concepts of iterated multiplication, addition, and function mapping are common across all spectrum of Maple usage. With older versions of Maple, we only had single-threaded versions of these commands. However, we recently introduced multi-threaded versions of these commands. They automatically split their calculations across all of the cores of your computer. Here, I'm simply adding the integers between 1 and 10 million together using the multi-threaded add. On a single thread, it takes about 22-23 seconds. However, if I allow Maple to use all of the cores of my computer, as you can see, processing time reduces dramatically, again giving you a real tangible time savings. And these newer multi-threaded versions of these commands are essentially drop-in replacements for their single-threaded versions. This means you can often get an instant performance gain with no work. We also parallelize the generation of Bernoulli numbers as well. These have applications in topology, Taylor series expansion, and the Euler Maclaurin series as well. So if I want to calculate these 4 Bernoulli numbers, Maple computes them in parallel on a single thread. If I restrict Maple to using one thread, it takes about 12.9 seconds. If I let Maple use 2 threads, it only takes 6.6 seconds. Again, that's a real tangible time savings. Now, there are other automatically multi-threaded functions in Maple, but let me put those to one side for a second. Let me talk about the memory management system. As I said, Maplesoft are committed to injecting parallelism deeply into Maple. We recently completed a multi-year project in which we rewrote the memory management system in Maple so that it runs in parallel. The memory management system is responsible for allocating and reusing memory. Typically for non-trivial Maple worksheets, it can run for anywhere from 5 to 20% of the time. Since we parallelized the memory management system, this often gives a real-world speedup of around 5 to 10%. That may not sound especially significant. However, when this is compounded over repeated calculations, this is a real tangible time savings. This makes a real difference to the user experience. Now, your computer may have a dedicated graphics card. That graphics card is used to accelerate the graphics in 3D computer games or CAD packages. A key feature of these processors, of these graphics cards, is that they have many cores, many CPUs. This, for example, is the Quadro FX 5800. It has 240 cores. Each of them runs at a relatively low clock rate, but, however, they're all optimized for parallelized matrix computation. In fact, they're all blazingly fast for matrix operations. CUDA is a technology which allows you to offload matrix operations from Maple onto the CUDA graphics card. It's activated with a simple software switch. So for example, let's say that I want to multiply two 4000 by 4000 floating point matrices together. On my i7 laptop, it takes about 3.8 seconds. Bear in mind this is a quad-core laptop, so this calculation is automatically split across 4 cores. However, if I flick that simple software switch and offload the calculation onto my CUDA graphics card, it takes less than 1/3 of that time, around 1.2 seconds. It's not only matrix multiplication which benefits from CUDA acceleration technology. All linear algebra functions which use matrix multiplication are also accelerated. I've spoken about a number of built-in parallelized commands. However, in Maple, we also let you write your own parallel programs as well. There are 2 different approaches, the task model and the grid computing model. I won't go too deeply into the advantages and disadvantages of each. That's on screen here. However, I do want to talk about the grid computing model in greater detail. So, the grid computing model allows you to write parallel programs on your local computer using Maple. That parallel program can then be deployed to a cluster with no changes at all. Maple manages the underlying task distribution, task queuing, and memory management. So, what does a program written using the grid computing model look like? Well, this is a typical grid computing program. I've highlighted some essential language features. What I do want to stress is that this is just the standard Maple programming language. So if you use Maple to write a simple program or script repetitive operations, then you should become comfortable with the grid computing model fairly easily. It's just the addition of a few extra keywords to launch calculation processes on multiple CPUs. So using these commands, we can launch calculation nodes on a local computer or a cluster. We can launch as many calculation nodes as we want, and Maple manages task allocation and task queuing. We can send and receive messages between nodes, and this is inherently thread safe and takes advantage of the recently rewritten parallel memory management system within Maple. And that brings me neatly onto the topic of SHARCNET. SHARCNET is a consortium of Canadian universities who have decided to pool and share high-performance computing resources. Researchers and academics across Canada can log into a website and run parallel programs using one of a range of software tools, and one of those tools is Maple. This infrastructure uses Maple's grid computing functionality. Essentially, researchers write Maple programs on a local grid and then deploy them to a distributed cluster with SHARCNET. Recently, one of my colleagues, Paul DeMarco, has used this infrastructure to run Maple on a Cray supercomputer on 16,000 nodes. Now, many of you may be aware of MapleSim. That's our tool for multi-domain modelling and control systems development. Typically, automotive engineers use MapleSim to model vehicles from the ground up. So everything from the interaction of the roads with the tyres, the transmissions, the differentials, the suspension system, the chassis dynamics, perhaps even a driver model as well. Often, you need to rerun these simulations repeatedly using small changes in the design parameters. This is known as a parameter sweep. MapleSim uses Maple's parallel programming technology to run these parameter sweeps in parallel. You can also run Monte Carlo simulations in parallel as well in MapleSim, again using Maple's parallel programming technology. Now, I've spoken extensively about how parallel programming and multi-core math can help you work more quickly and efficiently. However, that isn't always the case. Sometimes a parallel program can be slower than its single-threaded counterpart. For example, not all of a math algorithm may be parallelizable. That places a maximum potential speedup on the parallelized version of that algorithm. And there may be bottlenecks in inter-process communication and excess computation. Essentially, efficiently implemented single-threaded routines may be faster than their parallel counterparts, and for this reason, FFTs, or fast Fourier transforms, within Maple are single-threaded. We've generally found that for the typical use case for most users within Maple, single-threaded FFTs are faster than parallel FFTs. So, how are we going to develop this technology for the future? What are our developers working on? Well, as I said previously, we're firmly committed to the technology, the parallel computing, and leveraging that for the benefit of our users. The Maple kernel is essentially the Maple engine. It performs low-level computing features such as low-level math operations and interpreting the Maple programming language. It's currently written in single-threaded C. Silk is a technology that's essentially a parallel computing extension for C. This will be integrated into the Maple kernel, and this allows us to inject parallelism more deeply into Maple in the future. We've asked our sponsored research groups to deliver parallel algorithms whenever possible, and we're also committed to researching future technologies such as numerical accelerator cards as well. I'd like to end with a brief conclusion. I think I've demonstrated that Maple can help you work faster, more productively, and more efficiently with multi-core math routines and parallel programming, and we have the technology and the commitment in place to support greater parallelism in the future. Thank you for listening.